Hello everybody, hope all of you are fine. In my last class, I discussed up to the formation of haloalkanes. Today, I will start from chemical properties of haloalkanes. Haloalkanes are highly reactive because carbon-halogen bond is polar. If you think about this carbon-halogen bond, it will be delta negative and delta positive. So this bond is polar. And the order of the polarity of CH bond will be CF, then CCl, then CBr, then Ci. Now what will be the reactivity of this CH bond? Reactivity will be just the opposite. Reactivity order, this is the polarity order. Polarity order. Reactivity order is for chemical reaction. Ci greater, then Cbr, then CCl, then Cl. This is because Ci bond length is larger and has the minimum bondation energy. Now this type of haloalkanes generally undergoes three types of reaction. One is nucleophilic substitution reaction, next one is elimination reaction, and finally or last one, reaction with metals. In case of nucleophilic substitution, a nucleophile attacks the carbon atom having a partial positive charge of the haloalkane, and CH bond breaks with release of halide ion. If we draw the structure, then you can understand. Suppose this one is an haloalkane and this is delta negative and delta positive. From the back side one nucleophile will come and that will attack here, and finally there will be formation of carbon nucleophile bond, and this X will be the leaving group and that will form X minus. Now depending upon the structure of the alkyl halide, there are two types of nucleophilic substitution reaction. One is called SN1, that means unimolecular nucleophilic substitution reaction, SN1, and another is SN2, bimolecular nucleophilic substitution reaction. First we will discuss SN1 reaction. These reactions generally takes place in case of tertiary alkyl halide. So if we take one tertiary alkyl halide, then if we add aqueous KOH, then there will be formation of OH plus KBr. Now this one is an SN1 reaction. SN1. Now what is the mechanism of this reaction? The mechanism will be like this. First step, this is called rate determining step, and this is the slowest step. Slow step, and this is called rate determining step. Then there will be formation of one carbocation, step 1 plus Br minus. Next in step 2, this is first nucleophile will be added to this carbocation and forming our desired compound. So here nucleophile is OH minus, so I am writing here OH minus. So here formation of alcohol, tertiary alcohol. Now this is a two-step process. Okay, actually the mechanism is a two-step mechanism, and here if we write the rate of the reaction, and this rate will depend on the slowest, that is RDS. In RDS only It depends upon the concentration of alkyl halide. Not on the concentration of OH minus or base. So as in RDS, it involves only one molecule, alkyl halide, and the reaction is called unimolecular substitution reaction or SN1. So if the compound is optically active, then we will get a raceme mixture, that I will discuss later. Now what will be the order of reactivity? Order of reactivity will be, in case of tertiary it will be highest. So order is, tertiary will give the highest, then there will be the secondary, then there will be the primary halide. Next we will discuss the SN2 type of reaction, that is bimolecular nucleophilic substitution reaction, SN2. These reactions are generally happened in case of primary halides. If we take CH3Br and if we give aqueous KOH, then we will get CH3OH plus KBr. So this is a SN2 reaction, and the reaction is following the SN2 path. Now what will be the mechanism? This is a single step process. That is the first step. T hydrogen and OH minus will attack just from the back side of the CBr, that means halogen atom, and in between there will be one transition state. Here OH bond is forming and halogen is leaving. Both are delta negative, and this state is called transition state. Finally we are getting the product. Here if we write the rate of the reaction, here rate will depend both on the concentration of alkyl halide and OH minus. So as in the RDS step, this is the Swiss step or RDS step. As in the RDS step involves two molecules, therefore the reaction is known as bimolecular nucleophilic substitution reaction. Now in case of SN2 reaction, generally it is occurred in case of primary halide. If we increase the branching, or if you think about the tertiary bromide, tertiary alkyl bromide, if we take the example of tertiary butyl bromide, then if we think about the backside approach of the nucleophile, suppose we are taking OH minus, so here it is sterically hindered, there is no space to attack this OH minus, okay, so it will not follow the SN2 pathway, so better it will take place, but it will follow the path of SN1 mechanism. So in case of SN2, the reactivity order will be primary halide, with the reactivity order will be high, then there will be secondary halide, tertiary halide very low, reactivity order is very low. So in this way all of you can understand the substitution reaction. Now I will give you some examples of some substitution reaction. So first, if we take that CH3CH2Br, this ethyl bromide, and if you give aqueous KOH, Then there will be one substitution reaction and it will form ethyl alcohol plus KBr. And you have to remember this thing that we are using aqueous QH for substitution reaction. Next, if I take C2H5Cl and giving sodium iodide in presence of acetone solvent, then we are getting C2H5I plus NaCl. This reaction is called Finkelstein reaction. Next, we will discuss the ammonolysis reaction. Ammonolysis reaction. If you take any amine, take methyl iodide, then this amine will attack here and this bond will, this iodine, the carbon iodine bond will break and we will get CH3 methylamine plus HA. So reaction will not stop here because the lone pair is available to attack another methyl iodide. If there is excess amount of methyl iodide, again this methylamine will attack another molecule of methyl iodide, and then there will be formation of dimethylamine. If we take this amine again it will react with methyl iodide. Then again we will get trimethylamine. Plus HA. Next, this trimethylamine again will react another molecule of methyl iodide and that will form quaternary salt of amine. So in this way we will get a mixture of compound, okay, mixture of amine compounds, primary, secondary, tertiary and quaternary. So it will be very difficult to separate. Next we will go another type of substitution reaction. If we take the example of substitution reaction of alkyl halide by potassium cyanide, C2H5Br plus KCl alcoholic, then from here we will get C2H5Cl ethyl cyanide plus KBr. Next, if we take the silver cyanide, in place of potassium cyanide, if we take silver cyanide, what will happen? AgCl. Now, the type of the product will change. Here it will form C2H5NC plus AgBr. Why this is happening? This is called ethyl cyanide and this is called ethyl isocyanide. Now here actually cyanide, if we see the structure then we can understand it is an ambidentate nucleophile. So it can attack from both sides. Whenever we are using that this ethyl bromide, then this C minus is attacking here and Br is leaving. So in case of potassium cyanide, it is ionic compound. But whenever we are thinking about silver cyanide is an covalent compound. It is a covalent compound, so nitrogen will attack this ethyl bromide. So here we will get AgBr plus C2H5NC. That means we are getting isocyanate. So in this way we will get different product. Next example, if we take that silver nitrite C2H5Br plus C2H5Br plus AgNO2. So in this case we will get the product C2H5 C2H5 NO2. But if I take potassium nitrate, then we will get C2H5 ONO2 plus KBr here plus silver bromide. Now here, because of the same reason, here AgNO2 is a one type of covalent compound. If I write the structure, then you can understand. So here this nitrogen will attack the ethyl bromide, and finally we will get the product of nitroethane. But whenever we are taking potassium nitrate, it is ionic compound, it is covalent, and potassium nitrate is an ionic compound. So here O minus is free, so this O minus will attack, and we will get the product that is called ethyl nitrite. This is called ethyl nitrite. C2H5OL. Now hope you can understand this type of reaction. Next we will go about the stereochemistry of this type of reaction, that means SN1 and SN2. Before going that part, I hope that all of you remember class 11 levels stereochemistry. There I discussed one thing, that is optical activity. Now what is optical activity? It is the property of a substance to rotate the plane of a plane polarized light either in clockwise direction or in anti-clockwise direction. If it rotates, if the molecule or the substance rotates the plane polarized in clockwise direction, then it is called dextrorotatory. If it rotates the light in anti-clockwise direction, then it is called levorotatory. Next, we have to discuss the chiral substance or concept of chirality. The objects are called chiral if one object is the mirror image of the other, but they are not superimposed. Suppose if we think about our hand, these two hands, these are mirror image of each other, but they are not superposable. So they are called chiral substance. In case of molecule also, if we think about lactic acid or active tartaric acid, definitely if we take their mirror images, then these two images will not be superposable. Otherwise we can say that if a molecule devoid of any kind of symmetry, like sigma I Sn, sigma is the plane of symmetry, I is center of inversion, and Sn is the alternative axis of symmetry. If these symmetries are absent, then the molecule will be chiral. And these chiral molecules can rotate the plane of plane polarized right, so they are optically active. Now, one thing I have discussed, that is enantiomer. What are enantiomer? Enantiomers are the stereoisomers, have mirror image relationship, but they are not superimposable. Racemic mixture, then it is a 50-50 mixture of enantiomer, two enantiomer, and here the optical activity is lost because one up is cancelling the optical activity of the other. Now, this process of conversion of one enantiomer into a racemic mixture is called racemization. Next, we will discuss about dissolution. Dissolution is the separation process of a racemic mixture. Now, what will be the case of this stereo electronic concept or stereochemical aspects of the SN2 or SN1 reaction? Generally, two things we have to understand. One is retention of configuration, another is called inversion of configuration. In retention of configuration means that the special arrangement of atoms or groups attached to a chiral carbon has not changed during a chemical reaction. If the chiral center is not disturbed, then it is retention. And during inversion, the inversion of configuration means that the special arrangement of atoms or groups around the chiral carbon or chiral center has changed, and the new atom or groups does not occupy the original position of the group replaced. Then it is called inversion. Generally, in case of SN1 reaction, there will be racemization, and in case of SN2 reaction, there will be inversion of configuration. We can take one example like CH3 CBr, then C6 H13, and if we draw their Liouville formula, then you can understand. Now in this molecule, if we add aqueous KOH and apply heat, then what will happen? OH minus will attack from the back side of the halogen, and this bond will break. Finally, we will get a compound that will be like this. C6H13. Now, if we see their optical activity, this will be a minus isomer. It is rotating the plane polarized light in anti-clockwise manner. So, this is minus 2 bromo-octane. And this one is plus 2 bromo-octane. So here configuration of the molecule change, just reverse, and this type of things are also called Walden inversion or umbrella inversion. So this is an SN2 reaction. Okay. So in this reaction, this is a case of inversion of configuration that you have to understand. Next, we will discuss the example of SN1 reaction. If during SN1 reaction, if the molecule is optically active, we are taking this example CH3 C2H5. Molecule is 2-bromo butane. So this molecule may be either plus or minus, it may be dextrorotatory or maybe levorotatory. So definitely around carbon 4 different groups are there, so it will be optically active. So first in RDA state there will be formation of carbocation. So here will be one lobe. Now in second step the nucleophile will attack. Nucleophile, if we are taking the aqueous KOH, OH minus will attack from both the sides. Now in this case, as this carbocation is a planar, so in this SN1 reaction, the nucleophile can attack from the both sides, so it can produce two type of isomer. One will be this one, and another will be this will be OH and this will be OH. So we are getting plus butane to all plus minus butane. So this is called DL mixture. And it will be 50% D and 50% L. So this is called racemic mixture, and the process is called racemization. So hope you can understand the stereochemical aspect of this type of nucleophilic substitution reaction. So today up to this, thank you.